Hello guys, welcome back to my video channel. I have stopped in my previous video at this title, energy density spectrum, and I have defined the notion of the energy to be the integral minus infinity plus infinity absolute value of ft squared dt in case of a real signal. So if this energy is bounded, the signal is called an energy signal. So what is now the energy in terms of the frequency spectrum of the signal ft? So the inverse Fourier transform of ft is by definition 1 over 2 pi integral minus infinity to plus infinity f of omega exponential j omega t d of omega. Okay, and f of omega is the Fourier transform of ft. Now, if I will replace in the expression of the energy ft, so this ft square, I can put it ft times ft. So I put ft here, and between brackets we see the definition of the inverse Fourier transform. By reversing the order of integration, so I can put ft inside and bring f of omega outside, so I will get this expression, okay? But the term or the expression here between brackets, it is nothing but f of minus omega, because this is the Fourier transform of ft when I replace omega by minus omega. So we can finally write the energy as 1 over 2 pi integral minus infinity plus infinity of omega times f of minus omega. In term, if ft is a real signal, so we have f of minus omega equal to f star of omega, and hence the expression of the final form of the energy can be written as 1 over 2 pi integral minus infinity plus infinity f of omega f star of omega d of omega, and this gives what the magnitude of f of omega, because f of omega is a complex. So this is known as the Parseval theorem, which allows the calculation of the energy when we know the spectrum of the signal ft. So we have two options. We can integrate in time and get the energy when the expression of ft is well defined, and also we can evaluate the energy in the frequency domain when we have the spectrum of ft, which is f of omega. All right. So now the expression here of the energy, we can write it 2 times this, and we take the integral from 0 to plus infinity, since the function f of omega magnitude square is a real and even function. So we will be left with a term 1 over pi, the magnitude of f of omega square, and this will define the energy spectral density of the function. So we will define EF of omega to be this one, and the energy at the end will be expressed in terms of this energy spectral density EF in the form 0 infinity EF of omega d of omega, where EF of omega is defined by this. It means the term which is under the integral will be called the energy spectral density function, and the energy can be expressed in terms of EF as shown here. Right. So this is an example of a gate function ft, which is existing from minus t over 2 to plus t over 2. F of omega is the Fourier transform of ft. So it is a function of the form sine x over x. Okay. Right. So now if I will take the magnitude of f omega square and I will multiply it by 1 over 2 pi over all possible frequencies, So I will get, so this negative shape here will be up, okay, because we are taking the absolute value. So this is why we are seeing this like this, okay. So this is what we call here EF, okay. EF, when we take the integral from 0 to plus infinity, we will restrict only this part of this function, which is 1 over 2 pi, the magnitude square of f of omega, okay? So this is the EF over omega. This is this is EF of omega versus omega. Now we can also calculate the energy between two frequencies, omega 1 and omega 2. And what we are seeing here in this color, gray, you see now a surface between two frequencies, omega 1 and omega 2. So here we can say that this quantity EB, it's the energy contained from omega 1 to omega 2, or between the frequency omega 1 and omega 2. All right. Signals that have infinite amount of energy but finite amount of power, okay, we can calculate the power P to be the ft of the average 1 over t, the integral minus t over 2 to t plus over 2, ft squared dt, okay? So here we are integrating from minus t over 2 to plus t over 2, and we are tending the t to plus infinity. So all signals that are verifying this condition, it means having this power P, or the average power, less than plus infinity, it means a limited number, okay? In this case, we can say that the signal Ft is a power signal, So this is a signal Ft, and you see it is existing from minus infinity to plus infinity, so it is not limited in time. In this case, if we will integrate Ft squared from minus infinity to plus infinity, will be equal to plus infinity. So it is not an energy signal. Now, if we multiply Ft by the gate function, or the rectangular signal, rect of t over t, which is existing from minus t over 2 to plus t over 2, if we multiply ft by this rect function, we will get f sub t of time. And you see here that we have taken just a portion of this signal from minus t over 2 to plus t over 2. So here we write f sub t to be ft times the gate function, and we will call capital F of t of omega the Fourier transform of this signal. So now, if we are limiting this signal to the support of time from minus t over 2 to plus t over 2, here, if we will integrate this function square from this limit to this limit, of course we will get a limited number which is less than infinity. So this is what we are doing here. So we are calculating the average power when we tend t to plus infinity. So it is 1 over t integral minus infinity plus infinity, absolute value of f sub t of time squared dt, okay? And we will also calculate the energy of this f sub t, okay, because now ft now is limited in time. So it is by definition equal to this, and in the frequency domain, we can also write it in that form. And we are saying that here that the signal f of t is an energy signal because it is cut. It is only existing from minus t over 2 to plus t over 2. So we can say that the p, okay, it is 1 over 2 pi over t, the integral minus infinity plus infinity. Now the Fourier transform of this signal square d of omega. Okay. Because we see now a correspondence, the correspondence between the expression of p in time and the expression of the p in the frequency domain. Okay. So here we have a factor of 1 over 2 pi, which is appearing when we take the Fourier transform of ft instead. Okay. Now we will call the power spectral density P sub f of omega, the limit of 1 over t absolute value of the Fourier transform of ft elevated to the square. And this by definition will be the power spectral density of the signal. The normalized average power of the signal, so the P will be 1 over 2 pi, the integral from minus infinity to plus infinity of the power spectral density Pf of omega. Okay, and also it is an even function, so we will have this value of the power will be 2 times value from 0 to plus infinity Pf of omega d of omega. As an application, if we will focus on periodic signals, we know that the average power P will be the sum from minus infinity plus infinity ck square. Okay, and it is c0 square plus 2 times the sum from 1 to plus infinity ck. Okay, because the amplitude when k is negative is equal to the same amplitude when k is positive. So the Fourier transform of the generating function of the periodic signals evaluated at k omega 0 will be 2 pi, okay, absolute value of ck, okay, or the modulus of ck, or magnitude of ck. So now we can replace this inside the expression of P, which is given by this. We will get the famous results that give us the average power in terms of the Fourier transform of the generating function of the periodic signal. Now let us consider a linear time invariant system whose input is ft and output gt, and we will call h of omega to be the Fourier transform of the impulse response of the LTI system. So from the convolution property of the Fourier transform, we can write an output signal, the Fourier transform of the output signal g of omega to be the product of h of omega times f of omega. So the g star of omega, which is the complex conjugate of g of omega, will be the complex conjugate of this, and this will be h of omega times f of omega star. If I will multiply now g of omega here, okay, and I will replace G omega by H of omega F of omega. I will get H star F star. Okay. So this, by definition, it is the magnitude of G of omega square, and here we will have the magnitude square of H, and here we will get the magnitude of F square. As a result, so the EG of omega will be H of omega square times EF of omega. Okay. And we will have also, if we take the limit, so the limit 1 over t gt of omega square will be also equal to H of omega square times the limit 1 over t ft of omega square. It means that here we divide by t, and we tend the t to plus infinity. As a result, we will have the power density Pg of omega to be H of omega magnitude square times Pf of omega. So here we have two interesting relationships, one for the energy and one for the power. Okay, it means if I know the Fourier transform of the LTI system, I can calculate the energy density and the power density from those information.